Hi, everyone. So in today's video, we'll talk about finding the eigenvalues and eigenspace for a 3x3 matrix. And this example will be used in the diagonalization section in our lecture notes later on. So I have a 3x3 matrix right here. I want to find the eigenvalues. Step one is you first create the characteristic polynomial. So we begin by finding the characteristic polynomial, which is determinant of a minus lambda I for some scalar lambda, or lambda I minus a, same thing, determinant of, because you're subtracting lambda from the diagonal entries, everything else remains the same, only the diagonal entries have a negative lambda. And we will equate this to 0 to find the eigenvalues. Well, first let's calculate this. So I'm going to expand along column 3 or row 3, as this one has the most zeros, and this is entry A3, 3, and 3 plus 3 is even. So the cofactor for this entry is going to be -1, 3 plus 3 times the minor. So it's just basically the minor of that entry. Okay, so let's calculate this determinant. So I have -2, negative lambda, times the minor. So you hide that corresponding row, hide that column. You're left with the 2 by 2 determinant. And I'm expanding along column 3 or row 3, same thing. The entry is A33 times the cofactor. That's the determinant. Simplify this. -2, negative lambda, and I have, well, I can just, the determinant of a 2 by 2 matrix is just cross multiply. So I have 1 minus lambda squared, -9. And I try to, you can open this bracket and simplify. So what do you get? -2, negative lambda. I have 1 plus lambda squared, -2 lambda, -9, which is equal to -2, negative lambda, and I have 1, I have lambda squared, -2 lambda, -8. So I calculate I try to factor this, split the middle term, or you can use the quadratic formula, and you'll get lambda minus 4, lambda plus 2 as two factors. This is, if I just ask you the characteristic polynomial of the matrix, you stop here. Characteristic polynomial. To find the eigenvalues, equate it to 0. To find eigenvalues, solve for lambda. By making it 0, I get two values. Lambda equals -2, and lambda equals 4. Now, if we recall the multiplicity notation, 4 is appearing once, so 4 have multiplicity 1. -2 appears twice, so it has multiplicity 2. These are the eigenvalues. Now we have to find the corresponding eigenvectors for each of the eigenvalues. So this is step 3 of our solution. Once I have the eigenvalues, I separate, because I have to repeat the process for both of them. Eigenspace for lambda equals -2. Let's call this lambda 1. And same thing, same process will repeat. Eigenspace for lambda 2 equals 4. Okay, so what was the step for finding the eigenspaces? So we take the matrix A minus lambda I right here, and we, instead of lambda, I plug in -2 and augment it with zeros and start row reducing. So I'm just going to write it out so that you have access to these notes. Replace lambda in A minus lambda I by -2 and row reduce the augmented matrix. The augmented matrix. And same process here, same process for lambda equals 4. So when I replace lambda with the -2 and I augment my matrix with a 0, I'll end up with a matrix looking like this. So I will have 3, 3, 0, 3, 3, 0, 0, 0, 0. Augmenting it, I get this. Take a minute and write out your matrices and see if you're getting the same matrix when you replace lambda with -2 and simultaneously replace lambda with 4 on the other side. So you have -3, 3, 0, 3, -3, 0, 0, 0, -6, 0, 0, 0. Okay. You can use a calculator to row reduce this matrix. Use a calculator here. For the sake of keeping this video short, I'm going to get to the final stage and leave that work for you. Once you row reduce it, you will end up with a matrix that looks like this. As you can see, there are two identical rows. I can divide the first row by a 3, subtract it, and I have two non-zero, two rows of zeros. Similarly, I do the same thing. I row reduce. I'm going to write the final output, and I get 1, -1, 0. I have 0, 0, 0, 0, 0, 1, 0. You could move this last row above here. Doesn't make a difference to our eigenvectors. Okay, so now that I have the row reduced form, I will try to rewrite and parameterize the solution set C1, C2, C3. Parameterize number of variables is 3. Number of non-zero rows is 1. That gives me number of free variables, aka parameters, will be 3 minus 1, 2 for this case. Same thing here. Number of variables is 3. Number of non-zero rows is 2. Number of parameters will be 3 minus 2, 1 in this case. When I rewrite the system, as you can see, the first column has a pivot and the other two columns do not. So C1 plus C2 equals 0. C1 equals -C2, and clearly C2 and C3 are free variables. C1 equals -t. Right? Rewrite the system again here. So I have C1 -C2 equals 0. And in this case, I have one more equation which fixes my C3. So I have, when I rewrite the system, I have C3 equals 0. So this gives me C1 equals C2. So clearly C2 has to be the free variable. We have done this already in chapter 1. C2, when I start from the top left, I go down, this one does not have a pivot entry, it's 0. When I go down, this one has a pivot, C3. So C2 is free variable in the other matrix. Now, I have parameterized the solution set. So what do I get finally? So I have C1, C2, C3. I write it in the form of the parameters. C1 is negative t, C2 is t, C3 is s. Because I have two parameters, I should have two eigenvectors in my eigenspace. So I'm going to break it up based on the parameter value. So you have to break it up in such a way that each parameter gets its own vector. And when you add them, you get the vector back. In the other, for the other eigenvalue, we don't have to do this work because we only get one parameter. So I get C2 and 0. If I factor t out, I'm left with 1, 1, 0. If I factor t out on this side, I'll get negative 1, 1, 0, and I'll get s 0, 0, 1. And there we go. This gives me the eigenspace. So every eigenvector for lambda equals negative 2 will be a linear combination of these two vectors. How to write my solutions in the exam? Eigenspace corresponding to the eigenvalue lambda equals negative 2 is, it has two vectors, negative 1, 1, 0, and 0, 0, 1. If you recall, each eigenvalue has infinitely many eigenvectors, but they will be a linear combination of these two. Similarly, eigenspace corresponding to eigenvalue lambda equals 4 is just the vector 1, 1, 0. And you can also get one step ahead. Because it only has dimension, one vector in it has dimension 1. This one has two vectors in it, so it has dimension 2. And there you go. This is how you find the eigenvalues and eigenvectors or corresponding eigenspaces for a 3x3 matrix. Practice factoring equations and simplifying the roots. And that's the most tricky part for this topic. Okay, I hope you enjoyed.